I'm stuck recording in the basement until I can replace my crappy upstairs mixer. The one I'm using down here is pretty good. It's a Mackie 1402 VLZ3. In the endurance event, every ounce of extra equipment contributes towards the 64-ounce weight limit. Heavier equipment means less fuel and less endurance. So where on the Bumblebee can we save some weight? In our record-setting flight last May, we used stock Dubro clunk tanks. They weigh in at 6.4 ounces empty, but I think we can do better. A wet wing was suggested, but at 43 ounces of fuel, it's just not practical for a control line model airplane. Something like a wet fuselage occurred to me. There's a lot of empty space in there that could hold more fuel. I glued together a fuselage section weighing 0.6 ounces so I could experiment with fiberglassing the interior. I made some epoxy filler to give the corners a radius. It's a nasty, messy job, and already I'm having doubts about the approach. At the consistency of toothpaste, it's applied to the corners and smoothed in using a finger dipped in rubbing alcohol. I used 3/4 ounce fiberglass cloth, and I'm always frustrated with this stuff unraveling. The lid was easy enough to do, but for the rest of my life, I don't think I'll ever glass the inside of a box again. It's just too hard to work on. The glassing added 1.2 ounces, and that's before installing any hardware or plumbing. I discarded the idea of a wet fuselage immediately. I made another fuselage section with the intention of installing some sort of fuel bladder. I scrounged the flange and stopper of a Dubro clunk tank to be used for the plumbing. A 1.5-inch section of rocket tube was used to interface the fuselage section to the tank flange. For my first attempt, I chose a Glad bag as the bladder. It provides no fuel pressurization, and it's more difficult than it looks to install. See if you can spot my error. The bladder approach added 0.7 ounces including plumbing and needs no header tank to collect air bubbles. This is a big improvement over the wet fuselage. Adding blue food coloring to the water makes it easier to find leaks. We're all ready to test the fuel bladder. A squeeze of the fuel bulb will start the filling process. I installed the stopper beside the folds of the Glad bag instead of inside the Glad bag. With the stopper installed correctly, the bladder filled as expected. The bladder filled nicely, but you can see there is some unused space in the corners of the fuselage section. This significantly reduces the fuel capacity from the expected 43 fluid ounces. The fuel was allowed to drain naturally. An inspection shows the bladder collapsed in an unpredictable way, leaving some liquid inside. It's not hard to imagine a fold in the bag trapping half the fuel. I tried other bladders such as this balloon. Some were too heavy and some had too specific a shape. All were worse than the Glad bag at using the available space inside the fuselage section. All the bladders were tested with glow fuel. 24 hours later, all had survived with no visible degradation. Of course, I know rubber won't survive much longer, but it only needs to last for 4 hours. I wanted to reduce the risk of the Glad bag plugging up the brass fuel tubes, so I fashioned a stent out of a Vicks inhaler. By drilling holes in it, fuel could pass through the stent while it held back the plastic bag. Keith suggested I try making a custom tank out of Foster's beer cans and JB Weld. I don't know why Foster's, but okay. I've never worked with aluminum or JB Weld before, so this is all new. In fact, I don't even drink beer. It turns out that Budweiser has a better shape for my purpose, so I ended up with a selection of both. When you don't drink beer, it becomes an expensive way of purchasing sheet aluminum. I came up with this ingenious method of folding the aluminum to create a self-clamping joint. It turned out to be absolutely useless. You can't bend a beer can more than 90 degrees without risking it splitting. I had my doubts about brazing instead of using JB Weld, but since this was all new to me, I felt I had to try. As expected, the aluminum can is too thin to store enough heat to mount the brazing rod, so the can just burned through. By wrapping the beer can around a 1-inch dowel, I was able to flatten the beer can reasonably well. A bit of light sanding takes off the inner epoxy lining and the outer decorative paint. This first attempt was never going to be a tank, but I learned how to work with the materials. In order to prevent a fold from cracking the aluminum, I started bending it around a piece of brass. Matching folds allowed me to splice aluminum together to get a longer sheet. The fuel pickup is going at the rear bottom outboard corner of the tank. To make sure the fuel drains in that direction, the outboard side of the tank is slanted. It must be slanted down from the top to send the fuel to the bottom, and it must be slanted to the rear to send the fuel there. The combined slanting results from rotating the side along the axis created through these opposite corners. The cut lines are marked out using masking tape, and tin snips do the job handily. The front view shows the slant towards the bottom, and the top view shows it towards the rear. This balsa jig helps keep the tank in shape during construction. Plastic Sullivan clunk tank tubing is used because it is lighter than brass and compatible with aluminum. This aluminum clip will be used to hold the plastic tubing in the correct pickup location. The clip will be folded around the edge of the tank, but before we do that, a corner shield is installed to protect the plastic tube from being clogged with glue later when the side of the tank is installed. Here is the tube, clip, and corner shield installed. The same was done for the vent tube on the other side of the tank. All that's left to install now are the two sides. Each edge of a tank side has 2 tabs out and 1 tab in. The end of each cut is done with a 1/16 diameter hole to stop the cut from ripping further. All the seams of the tank are sealed with JB Weld. 3 large Budweiser cans were used, and I didn't need any Fosters. The tank weighs in at 1.4 ounces, but it requires an additional header tank, so let's call it 1.7. Here's 43 ounces of water, and it all fits into the tank. It takes ages to move 43 ounces of fuel using a fuel bulb. I'm concerned that the 4-degree angle I built into the tank is not enough. If we move the lead-out guide back and the plane yaws more than 4 degrees, the fuel moves to the front of the tank and the engine quits. I have plans to build another aluminum tank with more front-to-back offset, but this time using Bud Light so I can tell the tanks apart. I'm also concerned about the changing fuel pressure in a non-pressurized tank as the fuel level drops throughout the flight. You can see at the start of the flight the fuel comes out the tube quite easily. If the aluminum tank walls buckle even just a bit, you can see the fuel pressure change slightly. Finally, when the tank is almost empty, the fuel barely drips out. In fact, the engine might have to suck it uphill. And now for 1 minute of exciting math. Circumference is 2 pi times radius, so on 52-foot lines it is 327 feet per lap. Velocity is distance divided by time, so depending on our lap times, our speed can range from 41 to 65 feet per second. Centripetal acceleration is the horizontal gravity experienced by the airplane due to its traveling in a circle. It is calculated as velocity squared divided by the 52-foot radius. A g isn't really a force. It is simply the ratio of a particular acceleration compared with Earth's 32 feet per second gravity. Our horizontal g's range from 1 to 2.6. Don't forget we still have 1 vertical g to deal with. We used the Pythagorean theorem to calculate the total g's. We use the arctan trigonometry function to calculate the direction of the resultant g-force. So the plane, fuel, and tank can experience forces from 1.5 to almost 3 g's at angles from 45 to 69 degrees away from vertical. I am so used to experiencing gravity vertically that I find it difficult to visualize the resultant g-forces at their calculated angles. Instead, I physically hold my plane so the g-force points straight at the ground. This way I can more clearly understand what's happening. It is pretty obvious from this picture that without pressurization, the Venturi suction will have to lift the fuel out of the tank when it is less than 1/4 full at 6-second laps. The engine run will have to be field tested for fuel pressure changes. I suspect we'll need to lean the mixture each time we reduce the throttle and then gradually enrichen the mixture as the fuel level drops. This routine would be repeated many times throughout a 4-hour endurance flight. I didn't give up on the Bladder idea. This version is shaped like the aluminum tank and holds the same 43 ounces. We haven't decided which tank to use on our next endurance attempt. That will all depend on the field tests. I'd like to use the beer cans if we can get it to work because it behaves most like a conventional tank. It isn't designed for pressure and I don't want the weight of a muffler on board, but gentle pressure could be applied by attaching an inflated balloon to the tank's vent pipe if necessary. The Bladder tank has the disadvantage of unpredictability in the way the bladder collapses. Regardless of which tank we use, it looks like a weight savings of at least 4 ounces, which could add up to half an hour of endurance.